I'm Mr. Ish and I'm welcoming all of you to this video. Halogenation of alkenes. Why does it occur? When intuitively one would think it should not occur because of the electronegativities that are involved. But in this video we will examine why and how you can halogenate an alkene. Everything will start here with the representation of the alkene. X2 in the presence of carbon tetrachloride, room temperature or below room temperature, where the halogen can be bromine or chlorine. Br2 or Cl2. You don't do diatomic iodine, it's not favorable thermodynamically. You don't do diatomic fluorine F2 because it's too violent or explosive of a reaction. Br2 or Cl2, it works very well, and you have a product which looks like this. One bromine here, one bromine here, and notice how a addition of the bromine on both of those carbons but in opposite directions. And why is that? Well, it's called an anti-addition or anti-addition, and you have to remember this. It's an anti-addition. When you're halogenating an alkene, it's anti, but when you're hydrogenating an alkene, it's a syn. It depends on the mechanisms involved. I'll just briefly introduce you to what I'm saying right here. If you are doing here a alkene and you're doing a hydrogenation, H2 in the presence of a catalyst, let's say palladium or you can say platinum, in that case the hydrogen will add in a syn manner from the same side, either both hydrogens from above or both hydrogens from below the plane of the molecule to give you a syn product. And that's exactly what it is. When you're doing a halogenation, you're having a anti-addition, meaning it would look diagrammatically like this. One will attack from here, one will attack from here, and you'll have an anti-product with regards to halogenation. Hence you will see something like this, X over here and then X over here, and you can worry about the stereochemistry, but here we're only talking about the syn and the anti-addition in terms of this quick example. The halogenation is an anti-addition, so remember that. The reaction will occur from opposing ends of the plane of the molecule. Earlier I alluded to intuitively that this reaction should not occur, and what did I mean by that? If I'm looking at here at an alkene, which you know is a double bond, the pi bond here can serve as a nucleophile, and then you're looking here at a diatomic halogen. You have a covalent bond here. You have two atoms with the same electronegativity, so you wouldn't think that this can behave as an electrophile because it's neutral. Where is this electrophilic character coming from? Hence, you would normally not expect this type of reaction to occur because you have a nucleophile, but where is the electrophile? I'm not seeing an electrophile here, but there indeed is electrophilic behavior of this, and we have to examine that. After examining that, you'll see why the halogenation will occur, and it occurs in the anti-manner. Heterolytic cleavage and polarizability of that halogen-halogen bond will explain why this reaction occurs. We're looking over at our halogen bond. This right here is polarizable bond. It shows a high degree of polarization to it, and it also undergoes heterolytic cleavage. What does all of that mean? If you're looking at any given time at instantaneous dipoles, you could have a partial positive here, you could have a partial negative here, or flip it around either other way. Because of the electrons and how they're clustering around the atoms, you can have a partial positive here for an instant, you could have a partial negative here. Then you end up seeing this polarizability which lasts for a moment of time, but it exists. And during that period of time, you can see there's a bit of a partial electrophilic character, there's a bit of a partial negative character here, or nucleophilic character. So what you are seeing here, that this diatomic halogen can act both as an electrophile and as a nucleophile once it undergoes heterolytic cleavage. What does that mean? If you look at everything here with regards to the electrons which are involved, you have something which looks like this. And remember, a bond is represented by two electrons, so let me demonstrate that. When you're seeing a heterolytic cleavage, which is what you will see in this halogenation reaction, you will have an asymmetric cleavage of this bond. When this bond breaks, you can see this go with one and the other one is totally deprived of it. So what you're seeing is this, in terms of Lewis structures, because one halogen retained both electrons of that bond, you have a anion, and the other halogen did not retain any of that. So you have here a cation which develops, and it looks something like this. You see how the electrons are deficient over here, but they're complete over here. You have an excess of charge here, you have a deficiency of charge. That's heterolytic cleavage. Contrast this to homolytic cleavage. In that particular case, when you're looking at something like this, one electron will come with this, one electron will go with this. So what you will see at the end result is this. You will have that, two of these. Here you have an equal sharing of a broken bond's electrons, and you can see it right here. That's homolytic cleavage. We're not seeing that in this reaction here. We're seeing heterolytic cleavage. We're seeing these two species result, and hence they allow for this anti-addition reaction to occur. What we need to do is understand the polarizability and the heterolytic cleavage in play with regards to mechanism involved, and that'll be it for this particular video. Look over here at your alkene. If you look at it in terms of orbitals, this right here is your sigma bond, and here's your pi orbital, here's your pi orbital, and you have electron here and here, and this right here is your pi bond. But we demonstrate it in a shortcut manner as this. One of these is your sigma bond, but the other one over here is your pi bond. The electrons of this pi bond, your pi electrons, behave as nucleophiles. They have a nucleophilic aspect. They behave like Lewis bases. These pi electrons can behave like Lewis bases because they are electron pair donors, and that is what is going to be in play when you're looking at a bromine come into action, a diatomic bromine. We don't need to see this representation anymore, but you're understanding pi electrons here are behaving like nucleophiles. The electrons of your sigma bond are not at play at all. Let's give here a complete representation. These electrons are going to look for a electrophilic species. This right here, your diatomic bromine, is electrophilic species because of the polarization and the instantaneous dipoles. You have some partial positive, you have some partial negative, and it's looking for this partially positive bromine, and it's going to sever this bond in a heterolytic manner. When that happens, this is what you will end up seeing, and I'll show you. One of these bromines which are split away will be exactly what you would anticipate, an anion, because it will retain in a heterolytic manner both of the electrons. This electron right here, hence it has a negative charge. The other bromine which would have been split in a uneven manner, losing both of those electrons, which is positive, is what is going to attach over here, and you can think of it as being brought over here like this. You have your 6 electrons, and here is your carbocation which develop, but it's so instantaneous in time or so temporary that it's rather fleeting. You will see this will come over here, and you'll develop here a cyclic bromonium ion. We'll call it this, a cyclic bromonium ion, because it's going to have a cyclic structure, and it is going to be having full level of bonds, as you will see momentarily. It's not a transition state intermediate, but it is something which exists for a temporary moment of time, having complete bonds. And this is what it would look like. This bond over here, as you can see, is coming from the pi electrons. These two electrons over here, this electron have generated this bond. These two electrons over here will come and add over here, and you'll have this. You'll still have the 4 electrons existing, and you have your positive charge. Look over here, you have 6 electrons here, you have 8 electrons here, because this bromide anion has stolen all the electrons from the heterolytic cleavage of that bond. This bromine only has 6 electrons, hence it's partially deficient. 2 of its electrons are going to come over here and form this bond right here. This other bond is forming from the pi electrons, as I've already told you. This right here is your cyclic bromonium ion. This bromide ion now can attack in the opposite direction here, or it can attack here. Why was this anti? Because you had an attack here above the plane of the molecule, hence this bromine has added here. Now the other attack is below the plane of the molecule, hence you're seeing the anti. One is above, one is below. It's anti. It's certainly not syn, it's anti-addition. When the bromine attacks in either of these positions, as you can see right here, it will then displace that bond, and the 2 electrons will come and combine with this bromine which exists, and you will have your anti-addition of bromine, and it will look exactly like this. You have 1, 2, 3, 4, and then 2 electrons coming from this and going back. Here's your 1, 2, 3, 4, and 5, 6. You have complete electrons that you should see. 1, 2, 3, 4, and then 2 from here, that's 6. 1, 2, 3, 4, 5, 6. Here you have 2 of these electrons right here forming the bond, and you have 6 remaining electrons, hence you see them right over here. Everything here now has a complete octet. You have your anti-addition of halogen across the alkene via a cyclic bromonium ion. We can call it an intermediate, but it's truly not an intermediate. It's a short-acting species, but the bonds are for real. And you have your addition process go through completion. You have to remember all the electrons which are involved. The pi electrons here from the pi bond are going to attack the electrophilic bromine over here and generate this bond over here. 2 of these electrons are going to generate that other bond, and you'll form this cyclic compound. The bromide anion will attack from the opposing direction, and you will return those 2 electrons back to the bromine. You have your 6 here, and you have your 6 here. two of those electrons generating this bond from right over here. As you can see, these two electrons. Everything here is complete with regards to the electrons developed and demonstrated. The halogenation of alkenes is anti-addition, but the hydrogenation of alkenes, which I have not talked about, I've only alluded to, is syn addition. This is anti-addition. And that's it for this video. Thank you for watching.